Okay, so the objective for this lecture is to probably discuss a little further on what the simulator does. In the assignment you submitted, you would recall that there were input files. The input files were run by the XSim simulator, and then you viewed your results in REST Insight, So you had, but the simulator appears to be something like a black box. You just send the file to it. So what does it do? And that's what I intend to, at least a large degree, to achieve in today's lecture. So I'll be talking about reservoir simulators, and let me recap. This lecture is primarily not in its entirety, it's primarily based on chapter 19 of the book, Petroleum Reservoir Engineering Practice. I think the chapter is titled Reservoir Simulation. So in some previous lectures, I have talked about reservoir simulation, but the question is, why is it necessary to conduct numerical simulations of petroleum reservoirs? And what I have in bold fonts here is just to reiterate some things I've said in the past. Whereas the field can be produced only once and at considerable expense, a model can be run many times at low expense over a short period of time. So numerical simulation of petroleum reservoirs enables us to run a model, a full field model, considering different scenarios a number of times to a large degree arrive at an optimal development scheme for your reservoirs. So in other words, reservoir simulation provides a powerful tool for evaluating alternative reservoir management strategies, thereby making it possible to select an optimum management strategy. Of course, based on existing reservoir operating conditions, reservoir and operating conditions. And of course, you also put into consideration future conditions that you could envisage. The relevant question in the industry is no longer why simulate, but rather how to effectively and efficiently apply the technology of reservoir simulation to develop reservoir management strategies, optimize reservoir development, and improve hydrocarbon recovery. So take note of this on why we need to conduct numerical simulation of petroleum reservoirs. So as regards reservoir management, there are a number of questions that reservoir simulation can help us answer. And one is, what are the expected hydrocarbon recoveries under the current reservoir management strategy you are adopting, or an alternate strategy? What can the expected hydrocarbon recovery, how can the expected hydrocarbon recovery be improved? And let me hear from you guys. From what you've learned so far, what tools can you use to estimate hydrocarbon recovery? I like feedback from you guys. When I mean tools, I'm not referring to simulation tools. I mean, it could be analytical tools, it could be methods, it could be equations, but what are the things which you have learned which can be used for estimating or predicting hydrocarbon recovery?
Sir, are we looking at well testing tests
Okay.
Like the PTA.
So the productivity index.
Productivity index. Okay, that's an interesting one. Productivity index. Yeah. Then Cruz, you were talking about you were talking about well testing. Yeah, because one of the aims of well testing is reservoir management, isn't it? Okay.
Yes, sir.
Yeah, I agree. What else? Yeah, that can be all. What else?
Sir, please. Okay.
No, let's hear. I've not heard from the ladies. Let's hear from the ladies. Okay, okay. Somebody's. Yes, Chisholm, you deserve a malt. You deserve a bottle of malt. Material balance equation. Correct. In fact, that was the answer I was looking for before I continue. So Chisholm, good one. Material balance equation. Good. Of course, I'm not. Material balance equation is not the only thing. There's something Dr. Adeojo is going to discuss with you guys, decline curve analysis, you know. So there are a plethora of tools which you can use, but you would see that deliverability test. Okay, that's good. That's good. Yeah. Yeah, deliverability testing, good. Yeah. So it can give you some insight, even though deliverability testing is more into getting potential, you know, but I think it's related. That's good. Okay. So who is speaking? Who is speaking?
Read one, sir.
Yeah, read one. Yeah.
I wanted to ask, the decline curve analysis is the opposite of pressure transient test, right?
Is it different?
Like it's the opposite, like the
yeah. Oh yes,
opposite
yes,
of
yes,
pressure
yes, yes,
transient
yes, yes. Yeah, in broad terms, yes. Because decline curve analysis is one of the methods for rate, what falls into the category of rate transient analysis. You know, in well testing, we talked about pressure transient analysis. So there's the flip side, which is rate transient analysis, where we tend to take bottom hole pressure as constant, while during pressure transient analysis, we try to take the production rate as constant. That's just one of the major things, but you have a great point there, yes. Yes, that's some good understanding. Yeah, I would totally agree with you. Okay, AOF, IPR, okay. But you know, what you mentioned, these are all gotten from your deliverability testing, which is an arm of well testing. You know, for well testing, you can have deliverability test and then pressure transient tests. So good ones. So let me continue. One of the other things we could is the reservoir a good candidate for pressure maintenance? Should gas or water injection be used for pressure maintenance? So these are some of the questions because we could simulate, we could build a model and see if I inject water, what would be my recovery? What would my recoveries be like? If I inject gas or water, or if I do it alternately, there's alternating gas injection, WAG. And then, of course, even though I made it sound so simple, there's the issue of how many wells, how many producers, how many injectors, what's the spacing. These are things that can be explored. And number three, for gas condensate reservoirs, will gas cycling improve total recovery? So gas cycling implies that while you are producing, part of the gas you produce to the surface, part of it is sent back into the reservoir. So that's the cycle. So part of your produced gas is sent back to the reservoir, and it's used for volatile reservoirs and gas condensate reservoirs, volatile reservoirs and gas condensate reservoirs. Number 4, what's the optimum well count and well locations for development of new reservoirs? Is the development of a new discovery economic? And of course, now we are linking the economics to it. Under prevailing drilling, completion costs, operating costs, product prices, would the company be able to go into the final investment decision? What management strategies can be used to change or improve economic outcomes of new projects? What's the optimum rate? What's the effect of rate on hydrocarbon recovery? Number 7 is basically a reiteration of, I think, point 2. Is the reservoir a good candidate for secondary recovery processes? When do you initiate secondary recovery? Should it be pattern flooding or should it be peripheral? You know, what's the expected incremental hydrocarbon recovery? Of course, when you talk about incremental hydrocarbon recovery, if you're not starting out with secondary recovery processes. Number 8, what types of enhanced oil recovery processes will be suitable for the reservoir? When you have a number of enhanced oil recovery processes, you could even test them out via reservoir simulation and rank them on a technical basis and economic basis. Now, how is the reservoir performing under the current operating strategy? So number 9 is indicative of how you can use reservoir simulation to either identify problems or even prepare for future problems. Number 10, what are the uncertainties and risks associated with the planned or current management strategies? And as you talk about uncertainties, you need to talk about risk mitigation. So you see in chapter 19 of the book, Ezekwe came up with the classification for numerical simulators. I'm holding on to, I'm using his classification, but I'll make some comments on it. So numerical reservoir simulators are classified on the basis of type, reservoir process, and the formulation of the simulator. Just to be sure that you guys are following me, please unmute yourself, read out what I have underlined, just the underlined portions, one after the other. Can we do 1, 2, go?
Black oil
simulators,
Yes.
positional
simulators,
simulators, thermal simulators, chemical simulators, streamline simulators, dual process simulators.
Okay.
Streamline simulator and door process simulator.
Streamline is the last one.
Guys,
Okay.
Streamline simulators, chemical
Good.
processing.
Okay. At least I think everybody got to read that out. Okay.
Network is bad.
So I'm going to come back to this. I'm going to come back to this slide. I want to briefly stop share and share something else. Now, can you guys see my screen?
Yes, sir.
Okay.
yes, sir.
Now, look at the portion I have circled or I put a ring round. You see, it says simulation, isn't it? So for T-Navigator by Workflow Dynamics, you see that under the simulation, there are 3 things. You have black oil, compositional, and thermal. In a previous class, I mentioned that like Eclipse, they have their black oil and they have the compositional simulator. The black oil being Eclipse 100, and then the compositional being Eclipse 300. I don't know what the thermal simulator for eclipse is called. For CMG IMEX, they have, for CMG, that's Computer Modeling Group, they have IMEX, which is the black hole simulator. They have GEM, which is the compositional simulator. They have STARS, which is the thermal simulator. But one of the pros, one of the advantages of T-Navigator is that T-Navigator includes or encompasses the black oil, compositional, and thermal. So they don't have a separate simulator for black oil, a separate simulator for compositional, a separate simulator for thermal simulation. All can be done within the same simulation environment. And that's one of the things I wanted to point out to you guys. I will return to my presentation. Okay, so for black hole simulators, you see that oil, water, and gas are treated as separate immiscible phases. And I think that's the key for the black hole, as separate immiscible phases. And then I'd like you to take note of the types of fluids that this simulator is typically used for. So it can be used for dry gas and black oil reservoirs. And then the third one for immiscible processes. And remember that in reservoir engineering, I mentioned two immiscible processes, water flooding and immiscible gas flooding, So you could use this. And of course, when we say black oil reservoirs, you know what a black oil fluid is. Now, the next one is the compositional simulators, where oil and gas are represented as hydrocarbon components. So here you're looking at your fractions, your hydrocarbon fractions. Water is treated as a phase. This type of simulator is used for volatile oil. It's used for volatile oil and gas condensate reservoirs. And of course, this will be your go-to simulator for immiscible gas EOR processes. So I would like you to see, so that you know for each simulator which fluid type applies. The next one is the thermal simulator. And of course, thermal simulator is for thermal processes. And when you mention thermal, thermal is, so this is thermal is enhanced oil recovery. Thermal is EOR, but it's enhanced oil recovery processes which utilize either some form of steam flooding, steam injection, or in situ combustion. That should be the last thing which I would discuss, or which I will record under reservoir engineering. That's the very last thing. For chemical flood simulators, this is also enhanced oil recovery, but for chemical flooding, you are using polymers, surfactants. So this usually involves injecting chemicals to change the rheology of the hydrocarbon fluid, and in aiding the rheology, most of the time, the viscosity or the fluid is made a little less viscous than before, so it flows better. And then it also affects the wettability of the rocks, which goes along to influence your recovery. For streamline simulators, that's a different ballgame entirely. And for stream oil simulators, these are it's a simplified form. So the reservoir is treated in form of tubes. So you treat the reservoir, instead of considering it as full porous media, you look at it as a number of thin tubes. So it's kind of it's less computationally demanding as compared to a typical simulation, typical final difference simulation. So usually that's why it's used for upscaling. I'll talk about upscaling in a bit, modeling of for water flood, since anything that entails tracking flood fronts, it will work for that. Anything, especially when you have several fluids, and then it will just capture them as different streams of flow. In chapter 19, they don't discuss it beyond what they have as what they have here, but it's good to know. So I think what's important is that it treats the reservoir as a series of tubes, thin tubes, where basically what it's just doing is tracking flow, and usually the flow paths are colored to so that you can look at the progress of the flood front as it's either doing injection or as fluids are progressing in the reservoir. Dual porosity simulators. Now, so you see that it's used primarily for naturally fractured reservoirs. So for naturally fractured reservoirs, if you recall, I think this discussion on when we talk about carbonate reservoirs, when you're talking about secondary and primary porosity. So usually, to my knowledge, to the best of my knowledge, it's not that you have some simulators that are dual porosity simulators, but you have simulators that have the capability of modeling the reservoir as a two porosity system. So like for the computer modeling group software, when you are initializing your runs, first of all, they will ask you, is it a single porosity system or a dual porosity system? And don't worry, in the very last lecture for well testing, which I would record, I would make mention of dual porosity systems as it is identified via the pressure derivative plot, but at least it's good I've mentioned here. So just before I leave this slide, is everybody clear with what I've discussed here? Okay, so I want to take it that you guys are clear. Now, so the next thing, and I wouldn't spend a lot of time here. So the next thing is derivation of the basic equations for black oil simulation, black oil simulators. And permit me, I'll come back to this. Let me quickly share Ezekwes's book. Okay, so let me share my screen. Now, so this is derivation of the continuity equation in rectangular form. Of course, for you to mention rectangular form, this is in regular Cartesian coordinates. It could also be done in radial coordinates or cylindrical coordinates. And it says consider a rectangular block with fluid flow in 3 directions, X, Y, Z, as shown in figure 19.1, and this is figure 19.1. So figure 19.1 shows a grid block showing fluid flow in 3 directions. Of course, and this shows you direction. So this is X, Y is into the book, and Z is downwards. And then, so during a time interval, the principle of mass conservation can be applied on a block, so that's on the block shown in figure 19.1 to obtain the following mass balance. This is the same equation. This is the same way we went about it in the well test class. When we wanted to derive the divisibility equation. So I wouldn't spend a lot of time here. So basically, mass flowing into the block at any time minus mass flowing out of the block is equal to the mass accumulated in the block at any time at a time period delta t. So if you follow the derivation, what I'm trying to get at here is that if you follow the derivation critically, you would come up with a partial differential equation, and this is what you can see in equation 19.7. Let me highlight that. So let me reiterate, for this course, I am not required to, I'm not going to ask anything on derivation. Why I'm even going through this is so that we don't just talk about the tools, what goes down when it comes to how the simulator itself works, what are the background equations. So this is a partial differential equation. The F here is mass per unit area, and this is a concentration term. This equation 19.7 is the continuity equation for fluid flow in rectangular coordinates. And of course, a similar thing can be done in radial coordinates. So similar to how we went about it when we were deriving the divisibility equation. And note, the divisibility equation, when we went to derive the divisibility equation, we did a similar thing. We took a cutaway portion of the reservoir, of course, even though this time was in radial coordinates, and looked at flow into that sector and segment and flow out. In addition to the continuity equation, you would need, so this is going down to, going down to explain what that, the F is, which I said there was mass per unit area. So the mass flow rate per unit area in a given direction for any fluid is the product of density, is the product of the density of the fluid and its velocity. We're saying mass flow rate per unit. Yeah, Cruz. In simplistic terms, mass flow rate per unit area. And of course, this would so mass is what? Mass is density times volume, isn't it? And okay, no, this V is volume. So if you look at it, this still equates to so I'm just breaking this down so that you can relate what you have in equation 19.8 to what I've discussed so far. Sorry, is there any question? How about I've not lost you guys?
You haven't, sir.
No, sir.
Are you guys with me?
Yes, sir.
Yes, sir.
Okay, is there any
Yes,
concern? Okay. I know that I think two of you need to go for a class. But I think this session is recorded, so you can make reference to it. Okay, so let me clean screen. So what is being done in equation 19.8, 19.9, 19.10 is writing the mass flow rate per unit area for the different phases. Okay, Chigozie, go ahead.
Okay, I'm sorry. Yes, I was just thinking, how is it that the equations are translated into a form that can be like used in the software? Like, how do they go from mathematical equation to
Okay.
equation? Yes.
Good question. Good question, Chigozie. Good question. So I will just move ahead to answer that question. So I take it that we are quite familiar with this equation, so we won't be. But what I needed to point there, you see that the mass flow rate has been written for the different phases. The subscript here is oil, water, and this is gas. Do you guys know why you have 3 terms for gas? Chigozie, are you still there? Maybe you can bail us out here. Why we have 3 terms for gas? Or does anybody know why we have 3 terms here for gas? This is the equation I'm referring to, equation 19.10. Okay, so that we don't spend too much time. What's happening is that this is the mass flow rate for the free gas phase, while this is for gas dissolved in oil and then gas dissolved in water. And that's why you have, anytime you have RS is gas solubility. You know what we call gas oil ratio is actually gas solubility. So that just tells you that this is referring to a term where you are having gas dissolved in the oil. So I'll go ahead to address, yes?
I want to ask why oil formation volume factor is also there. Compared to the formula we just got, density times length over time.
Okay. So, of course, this tells you that, anytime the formation volume factor comes in is because we are trying to account for underground reservoir conditions, isn't it? Where are you still there?
Yes, I'm here.
Yeah, okay. So the question is, the difference, typically if you want to account for reservoir conditions, you multiply by BO, isn't it?
Yes, sir.
I want you to respond so I know you are.
Yes, sir. Yes, sir.
Yeah.
Okay.
But here we are dividing by BO. The reason is that this is density. Density and volume have an inverse relationship.
Yes, sir.
Yeah. So the reason for the BO, first of all, is because we are accounting for reservoir conditions. But why we're dividing by BO is because of the density term, because this is not the volume. So have I answered the question?
Yes, sir.
Okay. So the BO in the other terms here is simply because of, since you're accounting for gas dissolved in the oil, the BO still comes in here and here. with the BO here and BW here. Okay, so
Thank you.
yeah, you're welcome. So on the right side of the equation, on the right side of the equation, you now have on the right side of the equation, this is the concentration term. This allows us to bring in saturation. You see that? So this is oil saturation. So this is oil accumulated in the system, in the grid block. This is water accumulated in the grid block, and this is gas accumulated in the grid block. Now, so yeah.
Okay, so I'm sorry that I know that I have a pending question, but what exactly does concentration of a phase mean?
Oh, okay. No, it's just so what's concentration? Concentration is amount. So in concentration you are talking about, no, concentration is not, concentration is not a rate term. Concentration is related more to volume. So it's more like the amount of a particular solute or solvent so it's more like you're talking. So on the right hand side is the accumulation term. Remember, we said mass in, mass out is equal to accumulation. So yes, the concentration term is basically, so in what is accumulated, or what portion of that accumulation is oil, what portion of that accumulation is water, what portion of that accumulation is gas. That's how concentration comes in. So it sounds as if it's chemistry, but no, it's just yes. So it's more of a volume fraction term. That's what I'm thinking. So if you look at it as a volume fraction term, it makes some sense.
Okay, sir. Thank you.
Okay. So here, so it says in equations 19.11, 19.12, 19.13. So porosity, phi is porosity, and then these are saturation terms. A constraint applied to fluid saturation in the block, it must be the requirement, of course, what you have in equation 1914. If you look at equation 1915, equation 1915, equation 1915 is so I believe you guys can relate to equation 1915. So all what you have here, these are
last year.
what you have. So this is the accumulation term. This is a sink or source term. This, who is that?
Fingers are not changing.
Okay. So the Q naught here is a sink or a source term, referring to either production or injection. So let me make some progress so I can go ahead to answer Chigozie's question. So equation 1915 is the accounts for the oil phase. Equation 1916 accounts for the gas phase. Equation 1917 accounts for, no, 1916 accounts for the water phase. 1917 accounts for the gas phase. So you would see, so you could simplify those equations by canceling out the density terms. So you see that what you have in equation 1918, 1919, and 1920 are basically the equation in terms of velocity and saturation predominantly. So you Sorry, can you guys still see my screen?
Yes, sir. You can
Okay,
see
good,
it.
good. So the equations 1921, 1922, and yeah. Who is speaking? Oh, I thought somebody had a question. Okay. So equation 1921, 1922, and 1923 are those equations, but now written in vector notation. And of course, this is the, so bringing it in differential form, and then in vector notation, they are simplified as what you have in equation 1924. Fine. So why for the fluid velocity term can be broken down further by introducing Darcy's law. You know, if you recall what we did when we wanted to derive the diversibility equation, we needed a continuity equation, we needed an equation of flow, and then we needed an equation of states. You know, so here Darcy's equation is brought in, and then of course, depending on the form of the Darcy equation, this is in form of potential. Of course, potential is your pressure and then the gravity term. And all this will now take you to the equations you have in 1926, 1927, 1928. Now, so the question is, now this brings us to Chigozie's question. And permit me to go back to my slides. Sorry, just a minute. Let me share slides. Sorry, I'm moving in and out. Now, so the Chigozie's question is asked. Now we have the equations. Chigozie, please, can you ask your question again, the way you put it?
Okay, so how do you transform the mathematical equations
Yes, okay,
into a solution?
Okay, so thank you very much for that. So what is done is your differential equations are now solved numerically. They are solved numerically. And to demonstrate that, let me see, do I have a... Okay. Now, so Chigozie, follow me on this point. Says the equations I've shown you before are the basic equations for immiscible flow of oil, water, and gas, respectively. When written in the difference form, these are the basic equations solved numerically in black hole simulators. So, and Chigozie, do you have an idea of numerical solution of numerical methods for solving differential equations?
Yes, sir, but it's not deep.
No, just give me the shallow one. I'm fine with
it. There's one I know, the Newton-Raphson iterative method.
Okay.
What else do I know? I know that.
Ooh,